Okay, well, I'm Andres. Why don't you come here? So we're gonna talk about reactive programming. But before that, we wanted to do a little intro about ourselves. We know some of you, but not everybody. My name is Andres. He's Luigi. He's a true Italian. I'm only half Italian, but we have that connection. And we work at PCI. Some of you may know us by Power Costs, Inc. We are in Norman, and we do software for the power and a little bit for gas industry. In general, the utility industry is trading, and we've been doing it for quite a while. We are mostly a Java full stack shop. And we work on the same team. We have lots of teams. We have like 16 teams, agile. But we work together in one where we do things around architecture. And so this talk that we have today kind of came out of one small project like that. And we're glad that we can share. You want to add anything before we? Oh, the computer? Okay. Okay, sure. Oh, all right. Better? Yes? No?
Are you using an adapter?
No, direct. You want me to do something with my Windows? Let's do maybe let me take it out and then let me go all the way. Oops. Okay, we'll try that. Okay. So Luigi's going to do the first part, and then I'm going to do a little demo, and then we'll come back for the conclusions, and you can ask us questions, okay?
Okay, as Andres mentioned, we are in the engineering team, and we are trying to tackle some truly challenging technical challenge, which is breaking apart big software built in an old-style monolithic approach in architecture. One of the technologies was some of the research we did to try and find tools to break apart this software while keeping everything working. So a nice, progressive, safe, stable approach is in the realm of reactive programming. The way Isaac Newton put it is for every action there is an equal and opposite reaction. This is, we're talking physics, but we are talking breaking one system into many systems that somehow they need to communicate and keep a balance. And so if there is something that breaks, if there is a surge in information, the other system, the downstream system, needs to respond and to react. This is the quintessential example of a reactive kind of information flow. Twitter has a stream of information. If you connect to the Twitter APIs, there is a stream of information that starts when you connect and keeps flowing. You don't know how much, you don't know when, and might go down at any time. And reactive programming gives you the tool to manage these amount of information and complexity. In the real world, we don't just have social media. We have sensor data. In our world, we have power meters. Every 1 hour, 15 minutes, 5 minutes, every so often, they send out a signal measuring the amount of power that's going by. It's going through. And for us, it's a fundamental kind of information. Event sourcing and log consumption. Think of a cloud world when you have a certain amount of servers that they're entirely disposable, and you need to collect all the log from those servers and be able to parse them and be able to see what happened to that specific instance, when it spun up, when it died down. Social media, again, everything that is user interaction, everything that is, I think it's the next one, yeah. Everything that is user interaction. If you think about the quintessential example of streaming information is Kafka, and it was created by LinkedIn to model all the user interaction in a website, in their website. Search, click, queries, messages, everything inside a series of queue that were driving, then every interaction was becoming a message driving their architecture. How does it work? You have a system and you have an interaction in a system. This might be an HTTP query. This might be a user that has clicked a link. It doesn't matter. This interaction, this disturbance to the system creates a reaction, meaning that it creates some product. For example, the response to your query with the search results, a new page if your interaction is a click, but it also creates something that will cause a system downstream to do something else. For example, your search query on one end will produce a search result. On the other, will end up into the analytics database to be then aggregated and to produce some results telling whoever what the users are searching for. This is extremely good for us because it breaks down the complexity. You go from one monolithic system that does everything to many small systems that are highly vertical and focused on one task. Easier to maintain, easier to deploy, easier to scale. And that's what we're trying to accomplish here. Reactive is not no more something that is bleeding edge. Reactive is a consolidated technology, or at least a paradigm. We'll talk about technology in a couple of slides. It's a consolidated paradigm with abundant resources. You can find every sort of courses, tutorial, code examples. As always, not everything works right outside the box, and it takes a second to wrap your head around this new way of thinking. But I pointed out Free Code Camp is a very good resource, very simple way to take the first step into this world. And then we have a couple of major leading reactive implementation. ReactiveX, surprisingly, has been created by Microsoft and open sourced. It's used in production by a whole lot of big names, Netflix, GitHub. It's a very solid implementation, and you can find the same concept implemented in many languages. So whatever you write in, you can get a ReactiveX SDK for your language, meaning that whenever you start studying this, you have a knowledge that's transferable through languages, which doesn't hurt. You can see Spring hand in this because the style is the same as the Spring website. Project Reactor is another implementation. It's smaller, it's more lean, and it's not as multi-language as ReactiveX, but it has the great plus of the fact that it has been embraced by JDK. So not with the same name, but Project Reactor is officially part of JDK 9 and up, meaning that it comes right out of the box with Java. No libraries, no dependency management, nothing to worry about, it just works. It's pretty great. But in Java 8, they have a TCK that's very easy to install, deploy, and use. Reactive streams, and when you talk about stream, you think about nice, undisturbed water up in some mountain, is very similar to water. It creates a very nice and easy parallel. The main concept of the Project Reactor implementation is the flow. The flow is a stream of events that you don't know when it ends, and you don't know how many events it contains. Meaning that the flow is like you open the tap, and if there is water, it comes out, and you don't know how much and how strongly will pour out. And you don't know when the water is going to end. And the flows allow you to manage all this. You have server that's sending events, and a client that manages them. And you can interact with them. Why it's so good? We're going toward a world of functions, serverless. And the fact that until today, actually, today, you query the database, you get the data set, you put it in memory, you look through the data set, you produce whatever your result it is, and you send it to the client. And doing all these, you have to keep a result set from the database and the results you produced in memory. But if you think about functions, when you run a function, you pay computing power times memory. So keeping all this stuff in memory is very costly and ineffective. So what you want to do, you create a function that gets one row of your result set, digest it, process it, and stream a result. Meaning that you're going to use a very limited amount of memory. And this is natural, this is native to this approach. And the great thing about it is that once you have a lot of separate events, you can process them in parallel. And again, it does not add any complexity to your system. So you have a flow of event, but this is terrible. Sorry for that. In the real world, you have some cases where something either happens or doesn't happen. So Project Reactor has the concept of mono, meaning that this flow will contain one or no events. And it's a subset of flags, and you can know that once you pass this event, you're done with it. You can just close everything and go home. But what does it mean, processing events? What does it mean, managing those events? First of all, we talked about the fact that upstream you have an amount of events that you don't know how much it is. You don't know how many events per second you're going to get. For example, Twitter called their APIs firehose, which seems a very appropriate naming. You can theoretically, subscribe to all the Twitter tweets in real time. Everything that gets tweeted gets sent to you through a Reactive API, meaning that downstream, your client is going to get overwhelmed and crash and burn. So what do? We buffer. But even better, we have the concept of back pressure. So not just the client buffer, because again, you use memory, you fill up the buffer, and then you, again, crash and burn, just after a few more seconds. Back pressure means that the client can communicate to the server, hey, my buffer is full, I'm being overwhelmed, do something appropriate. That was it? Awesome. This is like magic. The client can tell the server, my buffer is full, I'm being overwhelmed, react appropriately. And there are different policies to manage back pressure. The built-in defaults are throw an error. For example, I have a flux on which I have some kind of information where I cannot lose any data point. So if I cannot process all of them, I need to stop, throw an error, and act appropriately. And then you can either drop the newest or drop the oldest. For example, if we're talking about tweets, I don't care about what has been tweeted 2 minutes ago. It's already old. So I can just drop all the old stuff and keep processing the new things as they come. And this is what really makes a difference. Andres got, and we show it to you, got deeper into this concept of back pressure buffer and created a smarter mechanism where the server, rather than stopping or throwing away events, just slows down. He has a producer-consumer architecture that reacts very intelligently to back pressure. What can we do with our stream? We can filter it. So I get a lot of events, but I only want the tweets that talk about Techlahoma. And so I can implement my filter, and in a very nice, clean, streaming, fluent syntax, make a series of filters and discard all the content I don't care about. And if filtering is not, okay, next. Mapping is another thing we can do. Think about transformation. I got all the tweets, and the tweets contains a lot of information. The author, the time where it's been tweeted, eventual tags, some meta information. I don't care about any of that. I only want one attribute that is the text of the tweet. So I can map my result in saying, okay, I have a full tweet object, let's map it to just this one property. Or when I have some more complex cases, I can do some transformation, even better, a series of transformation in order to make my input data in what I want to output. And again, we go back to the example we did earlier. Think about any green circle is one of the rows of my data set. I get the data in, I process it, and I stream results to the client. And this is a more complex example, group by. So let's suppose I have different kinds of data in my input. I want to separate them in different streams and pass them down to different processors. And we have a group by operation. Now, the real nice thing about those operations is that they are built into the framework. You don't need to invent, you don't need to build infrastructure, you don't need to maintain any implementation. It's just there to be used as part of the library. And now if you want to, now Andres will show you some actual code and some implementations.
All right.
Spring Webpack.
Okay, thank you, Luigi. So I'm gonna get out of here. I'm gonna go to my development environment. So before I show the code, I actually want to show you a little bit of how this streaming data is sent to the client. I have one client running here on my development environment. You can obviously do this through the browser as well. This is one of the things that was nice with Spring Boot is that we, for everything we do, we need to kind of secure and do even our prototypes in a secure way. So as you can see here, every time I move my scroll bar down, it just keeps going and going and going. It's streaming data as fast as it can to me. And so for us, we have, obviously, this is an example. We did something where we, each line that you see here is like a tick and a stock price. That's not really what we do at PCI, but it's a nice example of a time series. So I'm going to walk you now through the code for that, and I'm going to start on the server side, on the service itself, and then we're going to go take a look at the client. So we put this on GitHub. We have it on our slides at the end, so you can get it from there. So what I have here is I have a little Spring Boot application. We did this with Spring Boot. It's very easy to get going. Just requires a little class. And so what we did is we have, I'm not going to show it, but we have a JSON file that has a few prices. So imagine the price of one stock throughout one day, and we didn't have to worry about hooking this up to a real stock service for demo. And so we just took 1 day of prices, we put it in a little JSON file that we have here on the project, and then we read that file, and we just put it in a little in-memory database, and then we can emulate the service side getting data from the database. So that's all we're doing here, nothing too crazy or too fancy. So that's the boot, and then we have, in this case, a controller. It's a single controller. Our model is very simple. It's just prices, and the prices has an ID. It has the name of the stock, a timestamp, and a double. That's the price. This talk is not about that, but if you do check out this project, we're using Lombok. That's another project that is out there that gives you really nice ability to model POJOs without doing all the getters and setters. It does them for you. It's really nice if you're a Java developer. It's like magic. So if you notice here, I do have a get time, get ID, get price, but you look at the class, those guys are not there. How does it do it? All right, check it out. It's and you can see it from the imports. It's Lombok. And it does all the stuff, like it does the constructors, it does a bunch of other things. And we are using JPA annotations to then bind, do ORM, bind this structure to the database as well. So that's a little nice thing that we were exploring with as well when we did here, this. And then we have, we're using Sprint data to model the repository. And I do want to make a stop here. We have it on our slides. We're not going to cover it today. But the concept that Luigi talked about, it's kind of nice to make a pause here. So what we're showing you today is a reactive stream from the middle tier. So in our case, we're using Spring Boot. So RESTful, anything that used for REST, to a client. Now, a client can be a UI, another application, whatever. In the ideal world, like if we were doing this for real, we actually want to keep being reactive all the way to the source of the data, which is the database. Sometimes you are connecting to another service which is reactive, then you don't have to worry about that. But for us, if we were to actually code this in production, we do need to use also a reactive driver that will stream the data from the database. Otherwise, we still have the problem, right? Because we're like telling the database, give me this huge amount of data, and they're going to suffer. So you're supposed to keep propagating that signal all the way to the actual source of the data. It actually works like a physical flow system. Now, we didn't use it here, mostly because those drivers are pretty much readily available for NoSQL databases, most of them. So if you get Cassandra or if you get Mongo, they already have a reactive driver. The community, and if you go follow Project Reactor, is also developing drivers for more traditional SQL relational databases. I believe no Oracle, but everything else, yes. Oracle perhaps develops their own. So anyway, that's one point of note here. So nothing fancy here. So let's go down to the controller then. So I'm going to start from the code, and then I'll kind of work my way out of that. This is our mapping to the RESTful endpoint. So we have just a single get method. The route is prices and the name of the ticker, the stock. And this is one thing of importance. So we're using here Spring Boot, and they have a special type of enum that lets you do a stream JSON value. And that's what you were seeing on the client. And you notice that it has a special format where every row is a JSON object, and it breaks the next line. It's a new JSON object, so it makes it really easy to consume that data even if you don't use this on the client side. And then we just take one path variable is the name of the ticker. In this case, I'm doing Tesla. And so that's, again, nothing out of the ordinary here except for this. So if you've ever done RESTful APIs with something like JAX-RS, it's kind of the what you would use if you're a pure no framework lock-in. Typically here you either have a response object, or you have a POJO, an array of POJOs, a list of POJOs, maps. And so here this is the first difference when we are actually emitting a flux. So if you want your service to be reactive and stream, that's the first difference. It's a flux of prices. You could also do mono, but really it still doesn't quite make a lot of sense to emit a single thing and use reactive. It's kind of there for compatibility. So that's in the surface. And then I don't want to get into a lot of details about this, but we basically we have a repository where we have all the prices, and then we just get the prices for this instance of time. So we get it from the database, and then we collect them to a map where we have, for each hour of the day, the given price. So that's basically, again, if we were to do this in a real project, you would actually get a full service that will give you the data from the database in a stream kind of return. The next thing we do is, so just like Luigi showed, you have to have something that actually emits these components, right? So if it is very simple, this library has a lot of ability for you to turn, let's say, an array into a stream, an array into a flux directly. And we wanted to experiment a little bit with it, and I hopefully get down to those details where we could have different kinds of emitters. So we would have one emitter that just gets the items and sends them to the flux. And then we wanted to have a fancier, which in a way detected the back pressure and say, hey, I'm seeing that you're going too slow. I'm going to flip the frequency of my emission. Instead of emitting a price point every millisecond, like real-time high-frequency trading, I'm going to emit you a price every second. So we wanted to experiment. We have, for the systems that we use, the APIs, and this is very important as you're experimenting, or at least it was very important for us. So like any library, any framework, they have some set of assumptions. They work for most cases. So when you look at how they deal with back pressure, meaning like they are detecting that downstream the data is there's some sort of clog they can't consume. So they have three things that come out of the box. You have to do nothing. One is just error. Hey, can't keep up. Sorry, we're terminating this flux. That for us, and I would say for a lot of the cases, really isn't a good option, unless you're ultra conservative and want to preserve, not running out of memory, very basic things. The second one was you can drop the latest, which still doesn't quite make sense. And the one that would make sense to almost everybody, again, at least in those use cases, is you drop the oldest. So, if you're getting tweets, that's a perfect example. Who cares about old tweets? You can keep going, just start dropping, and that way you can buffer. For us, that one is A-okay, but we wanted to, instead of losing items, again, see, hey, can we experiment with this, where we will buffer, and we are okay buffering, we have resources, but not forever. So basically, we detect, we buffer, and then we flip the frequency, so we kind of have a little bit more control. And you could do those things. That's the moral of this story, and hopefully this talk. But you have to do a little bit more coding. So that's our emitter. I'll get into those details, and with that, we'll finish. And then here, you have a lot of control. Let me show you on this method. So their API is super nice. It's 100% fluent, meaning I can get a flux, and I can tell it what I want to do with back pressure, and I can tell it how I want to do what to do on cancel, on terminate. Everything can be chained. And we have used that, for example, here, where we would say flux, make it a push from my emitter, then do on cancel. I'm basically giving it a lambda expression of, if this gets canceled from the client says, hey, I'm done with you, don't want it anymore. For example, on the browser, if I push the stop button, what to do on that. And in our case, we're closing some resources. Our emitter is auto-closable, so we're closing it. If you terminate, if on error, you have all sorts of control. You can also do any of the operations that Luigi said, map in it, flat map in it to something else, group by, filter. You can do everything chain, and it reads really nice. We wanted to have some control here for experiments, so we ended up doing, delegating the flux into some methods where we do, we can control how we do the back pressure, whether we want to buffer or not, and we can control how we want to log. So, do you want to log on every request? So, if you are experimenting, or if you are in a scenario where you need to perform certain validations as you are about to emit data, perhaps security or control, can you see this item, can you not, then you have a lot of ability to, again, do that in a very simple, fluent API, okay? So let's get down to one example. So let's see if I kept the entire history here. Yeah, okay, so let me show you this. So, so here I'm on the server side. I didn't show it, but you can basically create a Maven. Go here and look at that. So you can create a Spring Boot run target, and that's all it takes to boot up your service. That's it all for you. That's a nice thing about Spring Boot. So I have that running, and then as I had a server connecting to it, you can see here I'm logging every item that we're sending to the client. And at some point, you can see here like the time between these is like a couple of millis. So it's going really fast, okay? Super, super fast for a few thousand items until, let me see if I can spot it. It's still going very fast. And at some point, you will see that we say we detected that yeah, we're going too fast, and then we are going to slow down. So let me see here. Have so many. This is every 1 second, so I already went past it. I'm trying to see if I find my line of log where it says. I probably need to see. Let's do this, old school. Can search. Okay, so here. Okay, well, it's not playing nice with me today. So let me see. All right, I'll try it again. So let's go here and let's actually try it live. So I'm gonna start a new client. Okay. And I'm gonna see if I can make it slow down. So I'm gonna stop this guy. And when I hit, and so if I go now to my server side on the console, I have two consoles going here. One is the, okay, I was on the, okay, so every time I just made a request, it's 12:12. And you will see kind of something a little strange. That's the max long. When you request an item on the client side, obviously the browser doesn't have this ability, but you could actually tell it, you can do more of a push-pull model where you would say, I actually am interested in getting so many items, or you can request unlimited. If you request unlimited, they use the maximum long number, which should be enough. That's why I couldn't find it. I was on the server side. So one of the things, and I'll get to the code in a second, this is the line that I was looking for. At some point after detecting that, hey, things are accumulating the client cannot keep up, then we switch the frequency, and we can do that in the way that I'll show you now. So let's get into that. So again, to set up the service, to summarize this piece, all we really have to do is to get some data, hopefully with a reactive driver, construct an emitter, and then do flux.push, and you just return that flux. That's all you need. So pretty simple setup. So now let's take a look at the server side, the last piece on the server side, which is the emitter. Okay. So on the emitter, you have to implement a method that says accept. It's a part of the interface. So you have to accept a flux sync. That pretty much is what happens when a client connects to you, right? So it says, hey, I want data. And again, here, and we're not doing anything too fancy with it, but you could play that dance that says, well, how many items did you request? Well, I give you that. Or, have you requested infinity? What you're going to do with it. So that's pretty easy. For us, what we do is every time somebody connects, we have a Java scheduler service executor. Again, we're prototyping here. That says, okay, every milliseconds get going and emit a price every whatever the emission interval is. And we have an enum that can emit at millis, at seconds, every minute. And so we start that, and then we call this, we delegate to this method, we emit. Whenever we have, and so the construct for the flux sync has lots of methods, and that's good and a little bit, I guess it makes it a little tough. You do have to read quite a bit of the documentation. So we, in this case, we're saying, okay, on request, which means every time a request, not an item, every time a request is made, what you're going to do with it. And then you can have on cancel, on dispose implemented. And so here, in this case, on request, you get a lambda that tells you how many items were requested as the argument. And here's where we have our logic to say, okay, if you're canceled or shut down, then just exit. And then we have something that can perform some additional bin counting, if you would, in our case, where we went, okay, how many items have we given it to you? How many items do we know that from the back pressure propagation have been consumed? And basically play with that rate of consumption versus production and flip the frequency. So I'm not going to have time to get into all the details again, so you can look at the code, but I think the important part that we wanted to show is it's not that hard to actually do some fancy, dancy business logic here. The generation, it just generates a price, so that's nothing crazy. And then again, our main customization, if you would, for this was, okay, we're keeping track of how many items were written to the flux, how many items were read, and again, we have some thresholds for that, and we're saying, okay, if you are above certain number of items that were already written, and you are overflowing, so basically have you overflown more than what our threshold tells us that we can overflow. So if you're doing that, then we're going to adjust, and we're going to print that message just saying, hey, I'm going to reduce your frequency, and we're going to change the frequency of our emission. So it looks pretty complicated, but if you spend a little bit more time looking at the code, it really isn't. So there's one more piece that I'd like to show. So this is on the server side. Again, if you want to do something simple, just a few lines. If you want to get it more complicated, not too terrible. And you can do pretty sophisticated things. The other side is the client. So and as you can see before I switch to that, so as you can see, I launched it at 12:12, so about 5 minutes ago. a minute and a half, and it was emitting at every millisecond. And then about a minute into it, it's like, oh, okay, you know, this is like, it looks like I overflowing my client, then I'm switching to emitting every second, okay? Which again, for us, that's really good because we're not losing data. All we're doing is mostly for sensor data is where like instead of giving you the raw measurements, if you imagine, you know, a sensor measuring the temperature of this room, for example, we are giving it the average temperature for that second as opposed to, you know, every millisecond. So not too bad, way better than losing data or dropping data in general for our type of problems. So, okay, so let's go to the client. Today we are in this code, we're mostly showing, you can also get Webflux on the client. We didn't have a lot of benefit for that, but you could do the same thing where you could have a buffer on the client. You could do all sorts of mapping operations. It basically comes with a whole flat map, group by, all that Fluent API. You can get it on the client through a web interface. It doesn't have to be a Java client. And so you can do that. We also have experimented with using just JAX-RS Jersey implementation on the client, and everything works fine. You don't have to get that fancy, but that's what we have. So we have a test that we wrote, and we're giving it our URI. We're setting up some login, and then we're constructing a client. I have it commented out here. So we're using authentication in BASIC in this case. We typically use a JOT token instead of user password. But you could get a client as simple as saying web client, create, and give it the URI. That would have no authentication, no HTTPS, nothing. For us, we encapsulated that here where we're using HTTPS. And then we're creating a connector with authentication. But nothing too fancy. You just get a HTTP client with some wrapping around it that deals with the buffering, the back pressure, and the giving you streams. So that's the first step. You do that. Then you tell it what method you want to call. For us, it was a GET request. You have here you have post, put, delete. We didn't have a lot of uses for anything that is not a GET, but you could do something for some posts. We are telling it the same thing that we did on the server side, that is a stream of JSON. And then you just tell it, okay, retrieve, and that's what we want to do. Again, here's where you could do some of the, transformations. You can transform it to a different type of flux. You can transform it to a mono. You can do some transformations on that. And here we are transforming it to a flux of our price type. Like I said, you could do, we have it commented out, but we could do some back pressure handling on the client side. So as a client, you also have some type of choice as to how you want to deal with this. And we've found out that that's a nice use of this library, that it kind of gives you control on both sides, on the server, on the client. Here we're doing something to delete elements, to do more things. And again, this, like I was mentioning before, if you look at the amount of methods you have available here, it's like 200 methods or more. So you could do a lot of stuff with it. Here we're only delaying each element to kind of emulate that getting behind effect for our demos. You wouldn't do that in a production workload. And then for each element, we're just printed that we received it, we subscribed, and everything goes. So this is important. A lot of people kind of get this going, and it's like, hey, nothing is happening. So basically, this doesn't, the way the library operates in their Fluent API, they kind of took the same thing as the streaming API for Java, where nothing happens until you call a terminal operation. So you could keep building, and until you call subscribe, actually, all you did was configure the thing for how you wanted it to operate. So this is it in terms of code. Like I said, we checked it in. It was super easy for us to get it going, but it was super complicated to really, took like a couple of days to get it all going, and then it took like 2 weeks of really playing with it and experimenting and tweaking it. So you can give that a try. And so we just have one more slide to finish, and then we can do questions.
But yes, this piece of code, think about streaming video. Basically, whenever the client cannot keep up and the video starts going, the server recognizes it and decreases the resolution of the video. You get a more grainy image, but it keeps flowing smoothly. And this is the same thing we implemented for whatever kind of data. The last slide is just some useful resources, starting with Andres' code in a GitHub repository, so you can check it out and run it. At first, it will look very, as he pointed out, very hard to understand, but once you step through, step by step, start debugging into both the client and server, it gets easier. I think we started by studying the theory, understanding reactive. It's a lot to take in, but I feel like I'm a software developer. Seeing some code running helps me a lot understanding the concept. Second link, Project Reactor. There is a reference and a very good explanation of the whole concept. Third and fourth link are 2 free small books about Reactive. Again, good reading. You can download the PDF and take a look at it. Eric's Java 2 JDBC, free JDBC driver to try and get into this world where everything is reactive end-to-end, starting with a reactive JDBC, ending with streaming events to the client through, I don't know, WebSockets, HTTP2, something like that. And finally, Eric's Java GWT. Even if you don't use GWT, it's a very good example and explanation of how the user mouse or the user interaction itself is an event source. It's not a click. It's an event in a constant flow of events. And it reframes your thinking about user interaction. It's very useful. And that's it.
I just wanted to make one more final comment. So one of the things that, at least for us, and hopefully you guys can relate, so we are a Java J2E shop. We have a fairly large enterprise application. So as you look into streaming, what we liked about this the most is like it's pretty easy, or the barrier of entry is pretty small if you have that type of setting. You don't have to get Kafka. You don't have to get all these other, super complicated, distributed, architectures in place to get into streaming. So it's super easy. Even if you don't use Spring, you could do all of this without Spring. And for us, that's really appealing. So you could embed it into JAX-RS type of setting if you already are using that. So we thought for us that was definitely a big plus, because once you have production systems and you kind of have a given architecture, the other stuff is super cool, nothing wrong with it. We actually like it very much. But for us, this was kind of an eye-opener that, hey, we could do all this stuff in Java without, going totally away from that stack. And hopefully you can, have a similar experience and can come to the same conclusion. That is not a huge barrier of entry. You don't have to change your whole architecture. There's some advantages of going with one more of a distributed architecture and having, if you need the scale. In our case, we don't need the scale of, 10 million consumers hitting us at the same time. So this looks like very promising. So I think that was it, right?
Yes.
And so we have a little bit of time for questions. Or we can just stick around after this and chat more informally. But wanted to thank you, everybody. Thank you, Techlahoma, very especially the guys at the JUG who let us do this presentation. We're very glad to be here, and we plan to be hopefully a lot more involved. And so thank you again, Star Space 46, and everybody who sponsors here. We've come to other talks, and this is a pretty awesome place to come and listen and meet people. So thank you again, and we'll go for questions now.
I'm not sure how to ask this. So when would you use Kafka versus not?
Mm-hmm. Yes, very good. Well, so there's a couple of things. So one is how many of these fluxes, if you would, you need to be producing, right? So for us, there aren't that many. So if you have a lot of different streams of data, of different kinds of data, that would definitely be something to consider. The scale too. I mean, we don't really need, so if you need to scale out and you need to make that service kind of have a life of its own and have control of its own, definitely very promising. More promising to use Kafka because that scales natively. This you still had to worry about, you know, if, for example, for us, if we were to embed this in our J2E app, then we got to guarantee that that thing can scale. We don't have that problem for what we do. We typically don't have, you know, millions of clients all taking at the same time. So I would say if you have the matter of scale, you definitely at least need to consider going distributed. If you don't, then and you have already some. If you want to get also the time that you have to. So for us, you know, looking at something that is a change of architecture like that, you're talking about months, years, versus, you know, you can get something very quickly. So maybe it's okay, but if you can, again, that's why we kind of got into that example where we are willing to sacrifice some accuracy, like the video thing, or for us, the time of the measurements, and get some protection, like, hey, we're not going to overwhelm the servers, we're not going to overwhelm the clients, so we're willing to sacrifice some scale, and that makes sense for us. If it, I don't know, you have to ask yourself your question. So I would say there's quite a bit of thinking that you have to do, but in general, I would say if you have internet scale or, you know, website traffic in the hundreds of thousands, millions, you probably need to, you know, lean more towards Kafka or any other distributed system.
Kafka will also give you persistency.
Persistence, yeah.
So if you need to persist one of those event queue in order to be able to replay, oh, right, thank you. Kafka will give you persistency. If you need to persist one of those event queue and be able to replay it many times in order to do, I don't know, different processing of this data, in that case, it's a very useful tool.
Yeah, there's all the stuff about delivery guarantees as well. We didn't care too much about, you know, making sure that, so you know, Kafka, you have some control over the delivery mechanism of these events, whether you want at most one, exactly one, at least one. If you're like into that kind of realm, that you definitely need like a true event kind of, you know, system. Anybody else?
Don't be shy.
All right. Okay, well, thank you again, and we are going to stick around a little bit more, at least get some pizza for us, and we can chat more informally. Thank you again.